A brief look at optimizing electrostatic precipitator performance, a short video featuring Dr. Kevin Linfield. Electrostatic precipitators, also known as ESPs, are used to capture particulate from a gas stream and are commonly used collection device for power generation, pulp and paper, mining, and cement plants. If designed and installed correctly, an ESP can collect about 99% of particulate in a gas stream before discharging through a stack. Incorrect design, on the other hand, can lead to problems such as lost product, the use of more or larger fans, or particulate buildup in locations that can threaten the structural integrity of supporting ductwork. Flow modeling and field testing are effective ways to ensure optimum ESP design and performance. Modeling is often done during the initial design phase, but both modeling and testing can be performed on an existing ESP. Combining the Institute of Clean Air Companies (ICAC) standards with manufacturing and final customer requirements, specific objectives of an ESP study will usually include ensuring that gas flow entering the inlet nozzle and each chamber is well behaved, minimizing pressure losses throughout the system, ensuring an equal flow split of gas and particulate to each chamber, ensuring proper mixing and interaction between any sorbent and gas, and minimizing ash deposition. The end result of the process is usually the design of flow control devices such as perforated plates, vanes, and baffles that can optimize performance and avoid costly problems. Both physical and computational fluid dynamic modeling are tools used in the analysis and optimization process. These methods can be used independently or in some cases together. The velocity profile within an electrostatic precipitator is critical to collection efficiency. While the profile can be predicted through flow modeling, it may be more cost-effective and less time-intensive to determine it through field testing. By traversing a vane anemometer through select gas passages in the ESP, a full velocity profile can be established. The results of this testing can be used to determine chamber-to-chamber flow splits, as well as identifying high-velocity regions that contribute to poor capture efficiency. Note the high-velocity regions shown in red on this slide and the uneven flow split left to right. For more information on flow modeling and field testing, please contact Airflow Sciences. Thank you, and have a wonderful day.